speed. And they really don't know how to explain it except for maybe one of these vortices sort of escaping out or vice versa. I think it's probably escaping out, like some of these vortices. By the way, in the superfluid, you have vortices as well, except even if it's not superconducting, except it's not something that carries magnetic flux. It only carries angular momentum, but otherwise it has some very similar properties. The other thing that apparently they've seen, for example, this is one that I saw a paper online, I guess it was this paper here, is they apparently see evidence for a very rapid cooling, and I think the way they explain that is that when you get the pairing taking place, it gives off massive numbers of neutrinos, and that releases enough energy that actually causes the thing to cool down quickly, apparently. And so there's a number of things that indirectly provide evidence for the existence of these superfluidity and superconductivity in neutron stars, essentially. Okay, the rest, I think I'm not going to worry about that for now. Okay, one thing before I forget, okay, I sent you a little info, it's probably incomprehensible, but about this guy A. Garrett Lisi's scheme or ideas about using group theory in Lie groups. This very massive group called the E8 group is a way of supposedly trying to relate, sort of tie everything together. There's another guy who's kind of another brilliant person by the name of Juan Maldacena. Now the thing that's interesting, Garrett Lisi is way outside the mainstream, and his paper has only been, it's on the archive, it's only been, I mean, it's been cited a good number of times, but not a humongous. It's been cited 131 times or thereabouts. If you contrast somebody with somebody that's a little bit more, much more in the mainstream, who's at Harvard, his name is Juan Maldacena, one of the things that he did is he came up with a way of supposedly mapping general relativity in a certain number of dimensions. I forget how it goes. It goes from 10 to 11 or vice versa. So in other words, mapping general relativity in a certain number of dimensions to conformal field theory in a different number of dimensions. So one of them is in 10 dimensions and the other is in 11 dimensions. Now why would that be useful? Well, apparently, I guess it's very exciting because it maybe gives you a way of potentially tying things together, but another thing that makes it exciting for people is that apparently it makes some things that are almost impossible to calculate in some limits for, let's say, using quantum conformal field theory. If you map it in this way, it becomes much easier to calculate using the general relativistic approach in the other different number of dimensions, and vice versa. In other words, sometimes something's impossible to calculate with the general relativity approach becomes much easier to calculate using conformal field theory. And apparently, as a mathematical tool, people have even used variants of that scheme, even in condensed matter physics, where they find a problem that's just like impossible in condensed matter physics, so they map it into something where you use general relativity, apparently, and they find, oh yeah, I can actually do some nice calculations based on that. Like there's a guy named Philip Phillips. He's a brilliant African-American physicist at University of Illinois at Urbana-Champaign. I've seen some talks by him where he's given some, he uses this scheme, or schemes like that in condensed matter physics. And so anyway, looking at general, so now, one of the things that, okay, principle of equivalence right here. So one of the things I guess I'll mention, since we kind of going back to special relativity, is that it turned out it wasn't so difficult to combine quantum mechanics with special relativity. And so essentially what happened was that it required some, well, I should qualify that statement. So for example, Paul Dirac, back in the 1930s, he was able to come up with a relativistic wave function, essentially, or a relativistic version, in other words, replace the Schrodinger equation with a relativistic equation that we call the Dirac equation. I should qualify that there were some complications in that he had to split up his wave function into like a column vector that had several different components, and essentially 4 components. And I guess maybe that had to do with the fact that you're trying to do this in a 4-dimensional space-time. You had to, there were some nuances associated with how do you construct fermionic particles that that still obey the principles of special relativity. And so there are all these things you have to somehow, you have to make sure that the thing is covariant under a Lorentz transformation and so forth. Now, before Dirac came up with this equation, there were what's one called the Klein-Gordon equation, which was more just a regular wave equation. And that worked okay if you're talking about bosons. In other words, it didn't work so well when you're talking about fermions, but it worked okay for bosons. Now, what happened in the Dirac equation is that when you split up the different components of your wave function into these 4 terms, I think what ends up happening conceptually is you think of them as being